The topic of the present lecture is robust statistical data analysis. Robust analysis is a branch of statistics which does not really belong to the classical area, but on the other hand it is not one of the most modern topics also, in that it has been around for some 50 years or more. Robust statistics deals with such kind of methods which are not seriously impacted by the presence of outliers in the data, small model misspecifications, violations of the parametric assumptions that we make. Now, we will primarily restrict ourselves today to the kind of methods which are outlier resistant, because robust statistics is a big field and we will be giving a talk in a short time. So, in effect we will be talking about why robust methods are needed and what are the solutions, rather than talking in depth about the mathematical nature of the robustness problem. So, here is our robustness theme picture. If you see, there is one cloud of observations on one side and there is another atypical observation on the other side, which may pull the inference in the wrong direction and can lead to erroneous conclusions. This is what we want to guard against. So, we will think in these terms that sometimes our data, the collected real data, will contain outlying observations. This is more true in the current age of big data, but yet we will want our methods not to be heavily influenced by the presence of those outlying observations. Our classical statistical methods do not have these properties, although our sample mean, sample standard deviation, least squares estimates in regression are very heavily used. They are extremely non-robust in the sense that they are highly sensitive to outliers. This is something we want to correct through robust methods. So, this is what we will look at. We have possibly a big data set which may be from a completely pure model, in which case we do not have a problem, but there may be some outliers which, in spite of all our efforts, may have crept in the data. So, we want our analysis to be such that it will give me a meaningful response even when the outliers are present. The point is, we also want to identify the outliers, and if we put a robust fit on the given data and then look at which observations stand out, that automatically gives us an outlier identification technique which classical methods fail to do. So, a little bit of history of statistics and robust statistics. Some of you may know that Professor R. A. Fisher is considered as the father of modern statistics, but the kind of statistics that we had in his time, they were all classical methods, methods based on sufficiency, methods based on maximum likelihood, which are fantastic methods, but they do not have the robustness property. So, after Fisher, perhaps sometimes in the middle of the 20th century, people started questioning about the usefulness of classical methods when outliers are present in the data. So, some of the pioneers who came along these lines include Professor John Tukey, who made the idea of exploratory data analysis familiar to us, Professor Box, who is very well known for the Box-Cox transformation methods. Finally, Professor Peter Huber, his 1964 paper in the Annals of Statistics on robustness of location estimators, people consider that to be the beginning of the formal theory of robustness. So, if we count the history of robustness from 1964, it is already more than 50 years old. So, here is a documentation of what just I verbally said. The theory of robustness started developing in the middle of the last century. In the 1950s, Box and Tukey came up with their ideas of exploratory data analysis, non-normality of certain necessary statistics and so on. Then came Huber. After Huber came another very bright statistician, Hampel, who finished his PhD at the University of California in Berkeley in 1968, and then came up with this idea of robustness based on influence functions in his seminal 1971 paper. So, here is the early literature, the literature by Box, Tukey, Huber and Hampel. These are still the Bibles of robust statistical data analysis. And we add to that the current canonical textbooks or the reference books on robust analysis. These include the books by Huber. At present, we have a second edition of this by Huber and Ronchetti. Then we have the book by Hampel and his associates, the book by Rousseau and Leroy, and a relatively more recent book by Marona, Martin and Yohai. At present, I think this is the most comprehensive book, the book by Marona, Martin and Yohai, that is available to us for studying robustness at relatively basic level. Okay, so I will try to present some real data analysis and try to convince you why robustness is important, why it is necessary. So, let us look at this data set. This is a Drosophila data. Drosophila are kind of fruit flies. That is not important to us, but the data, if you look at, it may be very well modeled by a Poisson distribution if the large outlier was not there. Look at the data corresponding to values 0, 1, 2, 3 and 4, we have frequencies 23, 7, 3, 0 and 0. If that were the entire data, classical method using maximum likelihood would fit very well to this. But we have one outlier at 91, and if you find the Poisson parameter using maximum likelihood, the fit that you will get out of this will be completely meaningless for future prediction. If you look at this, the blue bar gives you the observed data and the green bars gives you the frequencies for the predicted values if you do maximum likelihood after deleting the big outlier. But if the outlier was present, the predicted values are given in this red bar, which has no relation to the observed data at all. Even the big outlier is not modeled by this. Okay, next one. This is something that you may want to model using a normal distribution. It seems to have a nice unimodal shape on the right hand side of the graph, but there are two big outliers sitting in the left side, which would completely kill your analysis if you use your usual maximum likelihood estimator to model this. Next one, Short's data, also a very famous data set, was used to measure the parallax of the sun. But if you look at it, it has two moderate outliers on the right and one huge outlier on the left, and fitting a normal distribution using maximum likelihood would be suicidal for these data. Same thing here, telephone fault data, another famous data set, which has a relatively nice normal structure on the right hand side of the graph, but one very big outlier sitting on extreme left, which will completely ruin your analysis if you use any classical method. Okay, one more example. Here also you may be tempted to fit a normal model to this, but the difficulty is this, that now you can see that the data are bimodal. There is a second mode sitting to the right of your original mode, the main mode. So, here also fitting by maximum likelihood will not capture either of the modes and will might give you a solution which will not be at all useful for future prediction. Here is another example. So far we have been looking at normal examples. Here is one more which is skewed to the right, very far skewed to the right. But if you look at it, there is one observation very far out in the right tail, and that observation is enough to make all your classical analysis using the maximum likelihood estimator completely meaningless. All right, now from univariate data examples, we move on to bivariate data examples. This is Hertzsprung-Russell star cluster data. So, a plot of log temperature versus log light intensity, and this has a nice cluster here. If you fit simple linear regression, it would give you a nice fit if you were restricted to this part, but the data also has 4 big outliers on the upper left hand corner. If you do a data analysis using your classical method such as least squares using all the data, then your least squares fit will not give you anything meaningful. This is another data set, Belgian telephone data. So, in the lower part you have a nice linear structure, but something is going on in the central part, we do not know what. If you use maximum likelihood, once again you are completely clueless. Now, let us go back and look at this Hertzsprung-Russell star cluster data a little more closely. So, suppose I fit the least squares line to this. It goes through the center of the data like this. So, if you look at the residuals that come from this fit, the residuals for the outliers and the residuals for the good observations will be practically the same. So, if you do a plot of the residuals, let us look at this. This is a plot of the residuals. The 4 big outliers are sitting there colored in red, but you cannot tell them as big outliers from this plot. They are mixed with your actual data set. But if you use a robust method of fitting other than least squares, and here I have done so by what is called the method of least median of squares. If I get time, I will talk briefly about that later on, but this gives you a line which essentially sacrifices the big outliers in the top left and gives you a good fit to the remaining cloud. So, what happens is, if you do a residual plot now on the basis of these observations, then the residual plot will look like this. And what do we see now? Our big outliers are sitting at the top, the residuals are sitting at the top. So, the message here is that if you first fit a robust, use a robust method to fit your data and then look at your residuals, it automatically gives you an outlier identification strategy, outlier detection strategy, which a classical method cannot do. This is one of the major advantages of robust statistical data analysis. We can do the same for the Belgian telephone data, and if I do that, you see this is how the least squares line goes. It does not fit the general linear trend at the bottom, it does not fit the outliers at the top. It is a completely meaningless analysis, whereas the robust analysis based on once again the least median of squares that passes exactly through the lines at the bottom and completely sacrifices the lines at the points at the top. So, once again outlier detection will be very useful if I use an initial robust fit. So, what then is robustness? In particular, is it a parametric method or non-parametric method? Since non-parametric methods try to reduce the importance of parametric assumptions, in fact sometimes do away with them completely, people sort of tend to mix robust methods with non-parametric methods. But robust methods are not non-parametric methods. They are actually parametric methods, but what robustness people would like to call it is the statistics of approximate parametric models. In fact, if we look at the visualization given in Hampel's book, non-parametric methods fill up this whole ellipse here, parametric methods go along this strict straight line, but robust methods being approximately parametric, they operate on a band around the strict line. So, once again the point is small deviations from the parametric model are allowed, small deviations, but we still assume that the model is mostly correct, there are small deviations only. Okay. Standard robust methods for location, as all of you may know, median is the best known because it is sitting at the center of the data. To perturb the median, you need to disturb at least 50% of data. Until then, it remains basically unmoved. There are some other measures like trimmed mean, for example, Winsorized mean. Trimmed mean throws away some observations on either tail. Robustness people believe that the outlier problems are essentially in the tails of the data. It's outliers are generally a geometric concept and the tail of the data. So, we throw away the extreme observations and do a mean of the middle ones, then we are okay. In general, it works well. Then there is the generalized mean. Instead of taking the simple arithmetic mean, if we throw in an additional constant alpha, then depending on the choice of alpha, your mean estimate may be highly robust. Your estimate for standard deviation, a robust estimate of standard deviation, we can devise a robust estimate based on once again the idea of ranks or median in this case. So, the median of the deviations, absolute deviations against the median properly scaled, that gives us a nice estimate, nice robust estimate of scale. So, if we want to see how these methods work in actual practice, let us look at the Newcomb data one more time. So, this is the Newcomb data, one big normal structure on the right, two outliers on the left, and we fit a normal model to this by the method of maximum likelihood. This is what we get, a completely useless fit, but if we fit a normal model to this by using the robust methods that I just introduced, this is the fit I get. It fits the normal part ignoring the outliers. Okay, let us continue. This is the first introduction now to M estimators, wherein M estimation, instead of using simple estimating equations like summation xi minus theta equal to 0, we put a psi function to this which moderates the behavior of these deviations. So, Huber's psi was a function which looked like this. So, as long as xi minus theta remained within plus c and minus c, it gave full weight to this, but beyond that the method chopped off the tails. So, it could not give more influence than this value c, and necessarily the solution was a fairly robust one. But this is only for the location case. In general, what we would have is we would have some function psi which would depend on your theta and your x and would be devised in such a way that it would give a robust solution when you solve this. This is the basic idea of the M estimator. An M estimator is actually a maximum likelihood type estimator. For the maximum likelihood, if you take the derivative of the log likelihood, to get what we call the score function, and you replace that here, then you get the maximum likelihood score equation. The M estimators are just a generalization of that. So, in general we have a nice theory about M estimators. Using our central limit theorem, we have an asymptotic distribution of the M estimator, which is normal with a known variance which depends on the form of the psi function. Very nice theory, so it is easy to use. So, the point is that maximum likelihood is a great method. It is what we would like to call the cornerstone of classical statistical analysis, but almost always it has very poor robustness properties. In fact, if you look at the normal and multivariate normal distributions, in particular let us look at the univariate normal distribution, then the score equation for the normal mean is just this, summation xi minus theta equal to 0. You solve that, you get theta equal to x bar, the sample mean. The robustness problems of sample mean are well known. All right. Another interesting thing, at one point people used to believe that if we have to have a robust estimator, it must be obtained at the cost of asymptotic efficiency at the model. We now know that is not so. I will not get into the details of this, but if you use methods like, let us say, minimum Hellinger distance estimator, we can show that it has the same asymptotic efficiency as the maximum likelihood estimator at the model. And just for illustration, I look at the Drosophila data we looked at some time back, which had one very big outlier which made maximum likelihood completely useless. If I fit the method of minimum Hellinger distance estimator to this on the full data, this is the solution I get. Maximum likelihood, meaningless estimates, maximum likelihood with outlier deletion, good solution, but minimum Hellinger distance estimator with the full data, still good solution. So, the outliers fail to have any impact on the minimum Hellinger distance estimator in this case, and it is very often so. All right, it is the same graph we have seen before. Another idea, in likelihood we maximize summation of log of the densities. What if we maximize simply the sum of the densities? In this case, we would end up with an estimating equation which would look like this, estimating equation which will look like this, or generally we can put in some tuning parameter alpha, so in which case it will look like this. So, if I study this estimating equation, look at this. Here, if xi minus theta is large, it has a heavy impact. Here, if xi minus theta is large, I have an exponential term with the square of, with a negative of the square in that, which makes this term go to 0 much faster than this term increases. So, this cannot have an undue impact on your estimation anymore. Okay, some references to this. And here are some more examples. I will not get too much into how I got these are obtained by appropriate robust methods, but these are solutions, robust solutions of the data that I showed you before. This one is Newcomb's light speed data, this one is Short's data, this one is telephone fault data. In each case, the robust fit sacrifices the big outliers sitting at the tails of these data sets. And this one was the Melbourne rainfall data, to which a non-normal model was fitted, an exponential model was fitted. All right. So, this was Snapper's data, which was bimodal, and depending on appropriate generalized means, the solutions are much closer to what would be the mean of the, or the mode of the pure normal component in the left in this case. Okay. Here is another data set from survival data. Source is Efron 1988, and here the kernel density estimate has one component here and one component there. So, if you fit by a Weibull model, let us say mixture of Weibull model, it gives some weight here and some weight there. But if you believe in the robustness philosophy and want to fit this by a single Weibull model, it would fit this part and it would completely ignore or sacrifice that part. Okay, now, before we end, we will briefly talk about some measures of robustness. So, given a particular data set, the techniques that we want to use, how do we measure how robust they are? Now, we will talk about some of the measures of robustness that are used in the literature. Perhaps the primary among them is what we call the influence function. To explain the influence function, we will look at the quantities of interest theoretically in terms of the distributions. So, first suppose we have a class of distributions and any quantity of interest will be looked upon as a function of that distribution. So, for example, if I have a distribution capital F, then the integral of x times df is the mean. So, that we will call the mean functional, and this functional will be written as some capital T of this f. So, this T is a function from the space of distribution functions to let us say the real line, and we want to look at the stability properties of this functional T. So, for example, we want to find the characteristics of f, but somehow we are getting to see some g which is slightly different from f. In that case, T of g minus T of f is your Bayesian estimation. So, what we like to do is look at g as a contaminated version of f in the following way. So, let us define a contaminated version of f which is primarily f, but there is some degenerate distribution with mass at y filling in for the rest of the time. So, with 1 minus epsilon probability we get observations from f, with epsilon probability we get observations from this value y, and how does this functional T behave when applied on f epsilon instead of f, where my interest is in T f. So, essentially I want to see how fast the functional changes with this epsilon, and how do you measure the rate of change? You take a derivative with respect to epsilon, evaluate it epsilon equal to 0, that is the influence function of the functional T at y, and a robust statistician would like to have bounded influence functions. That means, you cannot change your functional by a whole lot through a contamination at a point y. Mean, for example, as a functional has unbounded influence function. So, mean is not a robust measure, whereas the median we can show has a bounded influence function. So, in terms of robustness it has good properties, it cannot be perturbed indefinitely. So, the statistical functional and influence function is this, as we just defined. The absolute maximum of this influence function is something that we call gross error sensitivity. This is also sometimes used in theory as a measure of robustness of a particular functional or a particular estimator. In fact, influence functions have other uses in statistical inference also, in the sense that the asymptotic variance of a functional turns out to be variance of an estimator turns out to be equal to the variance of the influence function. So, it has a dual role in both in robustness and asymptotic efficiency. And finally, the other measure that I want to talk about is called the measure of breakdown point. So, you have some distribution f and you want to find the characteristics of f, but what you are getting to see is a contaminated version where 1 minus epsilon percent is coming from f, the rest from something else over which you have no control. So, how big can this contaminating component be before your method essentially break down, your estimator runs away to infinity and all other kinds of bad things happen. And that proportion is called the breakdown point of the estimator, or the proportion of bad observations that the estimator can handle. So, influence function, gross error sensitivity and breakdown point are perhaps the three most important measures of robustness that are used in the robustness literature. So, we have now talked about the influence function, the gross error sensitivity and the breakdown point. These three are the most important measures used in the literature for measuring robustness of an estimator. So, with that we come to the end of this lecture on robust statistical data analysis. Thank you.